Right, hello Year 11. You are currently having a PSHE lesson that I totally forgot about. So I'm going to teach you about catalysts. I'm just going to get you to watch this little video, make some notes in your books. So just to make that really clear, what I write here is what your notes are going to look like. We're going to learn today about catalysts. We're still in the topic of rates of reaction, because you probably know that catalysts are chemicals that speed up the rate of reaction. So let's find out what we already know then. We know that catalysts speed up the rate of reaction. We know that catalysts are often transition metal compounds. But you know what? Actually, I'm just going to start. I'm going to write a definition, and this definition is what you have to learn for your GCSE. Okay. A catalyst speeds up the rate of reaction, and we're going to find out how now. Okay, a catalyst speeds up the rate of reaction by, and this is the really key phrase, providing an alternative reaction pathway with a lower activation energy. Now that phrase is vitally important. Okay, this is what the lesson was going to be on about today. I would have obviously shown you some demonstrations in that, but providing an alternative reaction pathway. An alternative reaction pathway with a lower activation energy. So catalysts, other things that we know about catalysts, they are often transition metal compounds. All right, they're often transition metal compounds. What else was I going to say about them? Don't get used up. Don't get used up in a reaction. So think about what that means. You can add a little sprinkling. I'm going to do that, little sprinkling of catalyst to a chemical reaction. The chemical reaction will go faster and faster and faster. And then you can filter out your catalyst at the end and use it again. So this is not going to go in the notes. Catalysts can be really super expensive, but you buy a little bit and it lasts forever because they don't get used up in a reaction. If you can get the catalyst back at the end by, separation techniques, filtering, you can use your catalyst forever. It doesn't matter if it's made of platinum, which a lot of them are. It's a transition metal. So they don't get used up in a reaction at all. So it's an absolute no-brainer in industry to put a catalyst in your reaction mixture. So we're thinking, right, this is part of our, how do you speed up a reaction? Well, there's loads of different ways. You can increase the concentration. You remember this diagram. You can increase the pressure if it's gases. You can increase the temperature, of course. You can increase the surface area of any solids, including any catalyst. You would always use a powder. And then you can add a catalyst. So yeah, concentration, that's definitely something you should do. Increase the pressure, yeah, increase the temperature. But if you can find a catalyst that speeds up the rate of your reaction and you can get it back at the end, man, you're gonna make a lot of money. All right? Because your reaction is going to go a lot faster. You can make a lot more product. Okay. Catalyst speeds up the rate of reaction by providing an alternative reaction pathway with a lower activation energy. What we're going to look at now then is what this actually means. Okay. What does this mean? Well, I'm going to represent this on a energy level diagram. So I'm going to draw an energy level diagram, which if you remember, energy, can you remember what goes on here? Little pause there. That's progressive reaction. Okay, so an energy level diagram. Let's do an exothermic reaction. So we'll put some reactants up here. And exothermic energy exits, so there'll be less energy at the end. Okay. So there's an energy level diagram for an exothermic reaction. This would be, as you know, this is revision. This would be the energy change. And we can see it's gone down here, it's exothermic. And what we've drawn on before is we draw a curve like this, which represents the activation energy. So the activation energy is from the reactants all the way up to the product. So I'm just going to write activation energy. Right there. Okay, so we know that to get from the reactant to the products, overall there will be an energy drop. Remember, I use the D of E analogy. There's some people up here and there's their campsite down here. This might be at 1,000 meters and this might be at 500 meters. So you could say, oh, it's 500 meters down to the campsite. But yeah, you've got to climb this massive hill to get to the campsite. You've got to put this amount of energy in, and that's the activation energy. There's a definition earlier in our notes. It's the minimum amount of energy required for a reaction to occur. You've got to walk to the top of this hill, and then you can slide down to the campsite. Okay, so what a catalyst does. A catalyst provides an alternative reaction pathway with a lower activation energy. Let me put that in everyday language. It gives you an easier way to get to your campsite. So what we can do on this diagram is we can draw on a curve for what a catalyst does. So all I'm going to do, from the same point, I'm going to draw a little bump underneath. This here, to the top of this curve, that is activation energy with catalyst. And you can see that it is a much smaller bump than without the catalyst. So I want you to put yourself in that situation. You're on D of E, you're on this little hill here, you know your campsite is down here, and you've got two choices. You can go over the big hill, which will take a lot of energy. You'll still end up in the campsite. Or there's a little door opens in the side of the mountain. Look at that little door opens. Are you going to open that door and you see a little hill? Gets you to the campsite, so it's an alternative reaction pathway, a different way of getting to the campsite with a lower activation energy. You're definitely going to go on that lower route. And more people are going to go on that lower route, and it's going to be easier to get to the campsite. All right, what this looks like in real life is really dramatic. You sprinkle a catalyst into a reaction, and the reaction happens just like that. It speeds up the reaction pathway by providing an alternative reaction pathway with a lower activation energy. So let me make this really, really clear today then, because I'm not in with you. You have to learn that definition. Learn that definition. And you have to be able to draw and label one of these diagrams. Okay? So let's just do a couple more of these diagrams. Let's just go through that, and then you're pretty much done. Okay. So you might have, you've got a reaction. They might say, this reaction is sped up with a catalyst. It's an endothermic reaction this time. Okay, so let's do an endothermic reaction. There's the reactants. Endo, energy is taken indo. That's useful, that. Energy is taken indo. Okay, so there we go. There's you with your rucksack on. There's your campsite. Here's the normal activation energy. Oh, man, we're not going to make it to the campsite. I don't know what accent that is. We're not going to make it to the campsite. You've got to put in too much energy. There's the activation energy. I don't know what that accent was. Sort of like a bit sort of American. I don't know. Right. We're not going to make it to the campsite tonight, guys, because even though it's only 500 meters to the campsite, we've got to climb all this way to get over there. I know. Let's add a catalyst. What's a catalyst, you might add? I can't remember. It's a chemical which speeds up the rate of reaction by providing an alternative reaction pathway with a lower activation energy. And this guy's down here. What does that mean? It means there's an easier way to the campsite. Okay, so you open this little door here, you walk up this way, you can get to the campsite, and you've only got to put in, there you go, activation energy with a catalyst. I think it's quite easy, this, isn't it? All right. It's clear, I hope, from this diagram that the catalyst provides an alternative reaction pathway, a different way of doing the reaction, that's what that means, with a lower activation energy. So you would have to draw a curve below the normal activation energy curve. So that would be for an endothermic reaction. All right. So in your books, you do one in the back of your books now because you've already got exothermic. So show you what an exothermic, imagine they give you this in the exam. They could ask you to label this axis, progress of reaction. They could ask you to label this energy. They could ask you to label the energy change, They could ask you to label the activation energy for the reaction activation energy, and then they could say, these are reactants, these are the products. Then they could say, on this diagram, draw a curve which represents how a catalyst works. You just go, oh, this absolute doddle, mate. All right. And then they could ask you to label the activation energy for the catalyst. You could either come across here and label it there, or you could label it here. Last thing I'm going to say, I think, probably not. That arrow has to actually match the top of that curve. I don't want any of this nonsense. None of that. It's got to touch the top of that curve. Okay. Now it would be lovely, wouldn't it, if I could show you a catalyst in action. You know what? I'm just going to pause this. I'm going to see if I can find one and do it on this desk. This is Dr. Dando's room, so I don't want to make a mess. I'm just going to show you one. One sec. Okay, I'm back and I've got a chemical. All right. I apologise in advance to Miss Dr. Dando if this goes wrong. Okay, what I've got here is some hydrogen peroxide. This is H2O2. Quite a cool little molecule. Looks like H2O, but it's not. It's got an oxygen, and two hydrogens like that. Now inside here, this is a reaction where hydrogen peroxide molecules bump into other hydrogen peroxide molecules, and they form H2O. So two hydrogen peroxide molecules collide with each other. They make water, 2H2O, and they make oxygen. All right? And that's happening inside there now. I promise you, there are molecules bumping into each other. But most of the collisions are not successful. Okay. So what we're going to do is I'm going to add a catalyst. So when I add a catalyst, so what we've got in here then, it's an exothermic reaction, let me tell you that. We're in this sort of situation. We've got an H2O2 bumping into another H2O2, and we want to form water and oxygen. But at the minute, as you can see, there's no bubbles going on in here. This is not fizzing, lots of oxygen isn't being produced because there is a high activation energy. All right? So yes, this is very, very slowly turning into water and oxygen, but it's going to take about 2 years. What I'm going to do is I'm going to add a catalyst, and what the catalyst will do, it will provide an alternative reaction pathway with a lower activation energy. And because of that, we will get more frequent successful collisions. Now, I've just realised I haven't written that in your notes just before this. So we're going to lower the activation energy, provide an alternative reaction pathway, and we're going to get more frequent successful collisions. The catalyst I've chosen is, let's have a little look at here, manganese 4 oxide, so that is MnO2. Transition metal compound, a transition metal compound. That's going to go in here. And what we should see is straight away, we should see lots and lots of fizzing. We should see lots of energy being released. Well, we should feel it. I'll let you know if it's hot or not. I could put a thermometer in. Right. Notice as well, might be able to see that, it's a powder. The powdered catalysts work better. Okay, you okay with what's happening then? There's only one reactant, but it's bumping into itself. And when it bumps into itself, it will make, let's have a look through there, water and oxygen. So, there we go. I'll put it through there. You can still see. So here's my manganese oxide. You don't need much because catalysts don't get used up. This is not a difficult lesson, is it? All right. So when this goes in, it will provide an alternative reaction pathway with a lower activation energy. You'll find out in year 13 what that pathway looks like. All you need to know is that statement. Okay, sprinkle a bit in and we should see oxygen being produced. There we go. So instant, isn't it? That's pretty cool, isn't it? So the reaction happened instantly. You can see also around the edge, you can still see the manganese oxide around the edge. I could filter that out and I could use that again and again and again to do this reaction basically forever. Reaction's almost finished. There's a bit of bubbles being given off. It'll settle down in a minute. And at the end, this will be water. That's what my reaction says. It'll be water. The oxygen's bubbled off. There'll be water. There'll be some manganese dioxide. I could filter that and drink it, but I'm not going to do that. Okay, you can still see the black powder in there. The catalyst has not been used up. All right, that is the end of your lesson. I want you to make these notes. I'm probably going to add a couple of little questions on this. So you're still doing your lesson now with Miss. Okay, you need to know this definition. You need to be able to draw these diagrams and label them. You've seen me using a catalyst. I've got more frequent successful collisions going on there. You've remembered that they're often transition metal compounds. If you didn't do triple last year and you just joined our group, I recommend you look up transition metals in your revision guide. Okay, transition metals. Anything else from there? No. Have a lovely time on the battlefields trip if you are going, and I will catch you next Monday. Yeah, sorry this has generated some homework for you, but that's just the way it is, isn't it? All right, nice one, everyone. See you next time.